So I discussed this old paper with Bertram and Leisesfeld. Yeah, we proved the following thing. We say that look at the F0 to Fm to be this ideal generated by a bunch of equations, yeah, polynomial, and they satisfy some inequality on the degree that the d0 is bigger than d21, bigger than dm. And assuming that this the projective scheme defined by this J is actually a non-singular variety of codimension E. Then the thing that we prove is that the ideal sheaf, not only the ideal sheaf, but you can also prove it for the power of the ideal sheaf, satisfies some regularity bound. And again, it failed to be regular. If the bound cannot be improved by one, then the boundary case is precisely the complete intersections. And the last part is due to my former student Xu Shang as part of his thesis. And now, and recall the regularity bound is saying something about the generator and relation about the minimal resolutions. Yeah. Okay. So say the generator is less than or equal to m if m is a regular, and then relation is all happening degree m plus 1, and then next step is m plus 2, etc. bounded. Now, and the fact that this involves only E equation, I think I mentioned this already, and this is roughly the prop. This all comes from the fact that we're working on the blow up of the projective space along X, and in here you have this exceptional divisor, and OP prime of minus AE. Yeah, if you call the projection map back to P, the F lower star of that is equal to IX to the A, at least for A positive. Yeah. So basically, you can try by monthly interpretation. One can say that the regularity of the ideal sheaf, which is the same thing as the regularity of the homogeneous ideal, can be computed by basically the minus AE here. I should be say E. Yeah. So there's some line bundle. You reduce the question into some question about computation of line bundle, and one can then apply codialar type vanishing theorem, or you can try to directly apply the method of multiply ideals and things like that. And that was how it was done in the case of the joint work with the Phoenix. Yeah. And now we left out a very obvious question we didn't answer. Now you have this ideal J generated by F0 to Fm, and it is contained in the homogeneous ideal I of X. And because the scheme is smooth in the projective space, these two ideal J and Ix is only differ at the origin in CR plus 1. And so therefore the quotient is something of finite length. And that just simply means that for high enough degree T, that Ix of T is equal to J of T. The degree T part will be matched for sufficiently high T. And we define the saturated degree of J to be the minimum T naught, such that J of T equal to Ix of T for all T bigger equal to T naught. And now, more generally, for a homogeneous ideal J, the saturation is defined by basically some sort of colon ideal. I mean, here it's just look at all the element F in S, such that the F, when you apply M to K, then it will annihilate the element in S mod J, and this is the saturation. Yeah, and okay, and now so our theorem with H and isocell is the following. Basically, we give a bound on the saturation degree, and the saturation degree in this setting is that this saturation degree is bounded by D0 plus D1 up to plus DR minus R. And more generally, if you have if you look at J to the A, the saturated degree of J to the A is equal to less than equal to A times D0 plus D1 plus DR minus R. And if some of the equation if m is less than r, then you can basically set some of the equation to be 0, and they don't contribute to the inequality. Now, to see that these things are somewhat a reasonable bound when look at the classical Macaulay theorem. So you have a bunch of homogeneous polynomial f0 to fr. Then suppose that these things generate a finite co-length ideal J. That means that in the projective geometry, this means that this R plus 1 hypersurface in PR, the common intersection is the empty set. And that's corresponding to a surjection from OP of minus DI to OP is surjective. And then we have a Koszul complex. And sorry, this should be just no minus 1 here, sorry. The ask to say whether J equal to I at the degree T is just simply asking whether H0 of this map is surjective or not. And so, but you can see that looking at this calculation, you can check that this is equivalent to saying vanishing by the chasing through the complex. This is equivalent to saying that if T bigger than D0 plus D1 up to DR, this would be the DR here, minus R. And then we have, so here we're just comparing the maximal ideal with J, and then the MT is equal to JT, even bigger than that. I mean, it's just a straightforward calculation on the co-kernel. And all right, now equivalently, you can see, suppose take G to be the kernel sheaf of the first map, then you're just asking for H1 of G of T vanishing, and then you can just chase through the breaking into sort exact sequence and chase, and then this is what you get. And one note that this is completely sharp, and if anything smaller, just because the HR of O minus R minus 1 is non-zero, one can see that the map is not surjective for anything smaller. Okay. So the bound we get essentially is asymptotically sharp. I mean, just simplify the Macaulay a little bit. Yeah, you take a hyperplane defined by some equation L equal to 0, and so this is a linear form. And again, you multiply Fi to be xi to di minus 1 times L, and J to be the ideal generated by the Fi. Again, J and the ideal generated by L is essentially equal. Again, they only differ at the origin by the same kind of calculation. And what you have is that the bound is saying that this thing is minus 2R, and basically you can do exactly the same kind of calculation here. Instead of a surjection from O minus DI to O, what you have is a surjection from O minus DI to minus 1. Basically, think of that, the map onto the homogeneous ideal generated by L. And the same kind of calculation will show that what happened here. So the actual bound is here, but what we get is something like this. So, and you can let A go up and things B go up and things like that. You can see that the bound basically is almost sharp, but not quite sharp in this case. I mean, I think it's still an interesting question to ask. What is really the optimal bound here? And I don't quite know the answer, and unfortunately, it's not so easy to do computation. So, so I really don't quite know what the expected answer to be, whether this thing is sharp or not. Now, if X is not smooth, then one really cannot expect a linear bound like this. For instance, that example that given by some simple thing like x to d, y to d, and x to y, cd minus 1 minus yu to yw to d minus 1 in the polynomial ring of 4 variable, And you can see the saturation degree is around d squared in this case, whether even though the equation all have degree d. So you need some hypothesis. Okay. So again, even with power a, we see that the number is still pretty reasonable. Now, this question is also related to symbolic power of the homogeneous ideal corresponding smooth variety also. I mean, there's some written commutative algebra comparing the symbolic power to the regular power. And I think together with Leicester and Karen Smith, we're using multiply ideal and asymptotic multiply ideal, things like that. We first obtain some non-trivial bound, and then this will improve by Hochster and Craig-Unicki to singular situation and positive characteristics. And anyway, for here, remember the symbolic power ideal is just simply this polynomial f in S as the order of f is bigger or equal to a for a general point x in X. And clearly the regular power is sitting inside the symbolic power. But one wants to understand how to compare them. Basically, in the case x is smooth, that Ix is only different by the saturation essentially is just the symbolic power. And then what you find is that the bound for the saturation degree is also given bound like this. So maybe let's just look at some example just for fun. For instance, this first example is take 3 distinct points, the coordinate point in P2, 1, 0, 0, 0, 1, 0, 0, 0, 1, and they're generated by the homogeneous ideal x, y, y, c, c, x. And the I to the a is completely equal to the saturation degree is just equal to 2a plus 2 in this case. And but now the actual bound is also pretty not so bad. Basically, you just have to worry about the case that you see the picture is like this. You have 3 points, and the secant variety is precisely 3 secant lines. And the singularity of secant variety is precisely this 3 points. You take the partial derivative of the equation xyc, then you precisely get the xyyccx, that precisely the defining ideal of the 3 points. I mean, so xyc is have multiplicity 2 on P2 of use of these 2 points. And now, but it's not in the it's in the second symbolic power, but it's not in the power because I squared and I is generated by degree 2 element. I squared will be the generator will have degree 4, but xyc is degree 3. So this thing cannot be in the it's not in the regular power. And this sort of thing happened. For instance, the same geometry happened for the so-called severe variety. Maybe the first case of the severe variety is the Varieties surface in P2, yeah, B2 of P2 in P5. And one can interpret this in the following way. You think of P5 as a set of all the 3 by 3 symmetric matrices. And then you have the Varieties surface, B2, P2, corresponding to rank 1, 3 by 3 symmetric matrices. And the rank 2 symmetric matrices corresponding to where the determinant of the xij equal to 0, here the xij equal to xji. And this is a cubic equation again. And the derivative of this cubic equation precisely gives you the equation defining the Varieties surface. And again, so the cubic equation is in the second symbolic power, but it's not in the regular power because the regular power, the ideal itself is generated by quadratic. Again, power would be generated by degree 4. Yeah, and this happened for all the severe varieties. So there are things like this. So the next case is the P2 plus P2, and there's a clay embedding, yeah, in P8, and then you have the G26 in P14, and then there's the E6 variety in P26. And this variety happened, in this case, they are the Seeger variety is a cubic, and they are boundary to the so-called Hasson linear normality conjecture that was proved by Sack. And this classification is precisely all the variety, non-degenerate smooth variety, non-degenerate smooth variety, such that the xn, then n is equal to 2r minus 4 over 3, yeah, something like that. And these are the boundary case of the so-called linear normality conjecture. And the theorem of Sack is that these are the complete list of severe variety. I mean, it's a classical theorem of severity, saying that the only smooth surface, non-degenerate surface in P5 that can be projected to P4 is the Veronese surface. To say they can be projected down, that means this Seeger variety doesn't fill up the whole space. In this case, it would be a hypersurface. In fact, the only thing that can be done, can do that, is the Veronese surface. And Sack theorem completely generalized a severity theorem to higher dimension in general. And again, in each case, you can see that the symbolic power is not, second symbolic power is not equal to the regular power. And then same thing, the power of the cubic equation showed that the how far away the regular power from the symbolic power was. Okay. Okay. And the next theorem is about just about reduced curve. And in this case, that one can, assuming that, again, the philosophy is that Casanova Mumford regularity control complexity in a lot of computational problem here. So if you know that the ideal is M regular, then again, you can control the saturated degree. In this case, the saturated degree is bounded by A times M. And in fact, this bar is sharp. For instance, let's check it for rational normal curve. Okay, the key ingredient of proof of theorem 2 is the so-called the Eisenberg Buchsbaum-Eisenberg complex. So what they are is something like this. So suppose you have a local complete intersection, then locally that this thing would be generated by a Cousin complex generate the ideal. The Buchsbaum-Eisenberg complex is the natural resolution of the power of the ideal. Yeah. And now, I mean, this thing is no longer defined by regular sequence, so it's not so, it becomes less obvious how to compute this minimal resolution for the power of the ideal. And basically, the Buchsbaum-Eisenberg complex is sort of kind of like the Igor-Norgov complex in some sense. They compute, in this case, what the power of an ideal is, how to compute resolving the power of the ideals. So let me start out by some projective geometry of the projective space bundle. So let's say E be a locally free sheaf on some, say, smooth variety Y, and you have something like this. Then you have the Euler sequence on P of E. The M is just simply the relative cotangent bundle twisted by 1. And you have the Cousin complex resolving O of the projective space bundle. And you twist it up by A plus K minus 1. And then you push down. And one check that the push down complex for A positive, and this thing would be a surjective exact complex. And you get something that looks like this. That is the color complex, or the push down complex looks like. And now, so to explain the Buchsbaum-Eisenberg complex, one needs the so-called Searle power of E. And this is, say, the representation. Sometimes can be a symmetric group can be think of as corresponding to partition. Here is the A11111 K minus 1 of the 1. And the Perry rule is saying that the definition as A1 K minus 1, this is the representation of E, either GLN representation or symmetric group representation. And this is defined to be the kernel of the complex that we define, basically. And also equal to, because the complex is exact, the kernel is equal to the image. And you can also compute that by using the complex that we're cutting from upstairs on the P of E, and it's just is equal to push down of the M bundle upstairs, the exterior power of the M bundle tensor with O of A. Let me, before I go on, I think it's maybe useful to list some basic property of this bundle as A1 K minus 1 of E. If K equal to 1, you just get the symmetric product. If K equal to 1, and if A equal to 1, you get basically the exterior product. And in general, it has some kind of obvious property like the following. Because all the group involved, I'm not category 0, everything is reductive. So basically, this sort of splitting is always the direct sum splitting. So we see that the symmetric product of E, dash K of E, really split into the kernel and the image. And then, so we get into the splitting here. And if you choose it by L, I mean, this thing is homogeneous of degree 1, L is the homogeneous degree 1, and this thing has weight A plus K minus 1. So again, it just behaves in a very normal way. And for us, maybe the calculation one need is that if you look at the direct sum of line bundle, you look at this shear power of E, and then the regularity is precisely A D0 plus D1. I mean, the thing is obviously the regularity is less than equal to that, but you can see not so hard to see that that line bundle is really a direct sum man. So, okay. So these are some. So now let me give a construction of the Buchsbaum-Eisenberg complex, and then instead of using the original proof, which is more commutative algebra, I mean, the way we're going to do it will be very similar to Kempf construction of the Igor-Markov complex. Essentially, you're going to go up to getting some Kouzou complex, and then you push down, and then the push down will eventually we'll see that will be equal to the Buchsbaum-Eisenberg complex. So let's start out with this J. J is, remember, is the let's start out with F. Yeah, then the symmetric algebra of F. You have a presentation of this coherent shift F, and there is a quotient of the symmetric algebra of E naught. So describe F is enough to describe the kernel, which is a homogeneous ideal, and this homogeneous ideal is precisely given by generated by all the degree 1 element come from the map E1, E1 map to E naught. E naught is the degree 1 part of the symmetric algebra. So this defines the ideal J. And if you, in terms of Prosh, then I'm basically saying the P of F is a closed-up scheme of P of E naught, and they will be defined by linear form, derivative linear form. And they're just looking at the map is just simply given by the following composition. It go E1 to E naught choose by -1, and then the -1 have a natural map. E naught tensor O -1 come from the Euler sequence and had natural map to OPE of the E naught. And the image of this composition map is precisely the ideal of P of F. I mean, it just follow from the description that you gave before. And now one want to talk about the blow up. And so in the case of a blow up, since X is local complete intersection, then the symmetric algebra of the ideal is equal to the Riesz algebra. I mean, in general, the symmetric algebra will always map onto the Riesz algebra, but may not be equal, but for the case of local complete intersection, it's a non-trivial result that in fact the two things are equal. Yeah. I mean, you can find a proof, for instance, in Fulton's book on and Lang's book on Riemann rock. Okay, let me continue with the construction. So you start out with I of x, and suppose I of x is given by this quotient of E. X is something defined at codimension E, a smooth subvariety of Y, and given by this rank E vector bundle. And X is of codimension E in there. So locally, this is a local complete intersection. And then the P of Ix, that is the same thing as a blowing up because of the symmetric algebra equal to the Riesz algebra. And then we see that then we're going to compare this with the, we want to find the equation of the blowing up on P of E. Now, from the Kousou complex, you have the Kousou complex resolving M, and given by the top row of this diagram. And we have the map alpha that map into the ideal of blowing up inside P of E, and not so hard by direct computation, local computation, that the composition beta with alpha is equal to 0. Well, what that means, that just simply mean that the map alpha factored through M, and therefore you have seen that you have a map M map onto the ideal sheaf of Y prime, where Y prime is a blowing up of X along, bringing Y along X. Now, so what we see is what we've done is the following. So suppose X is locally is a zero section of a vector bundle on Y of rank E, then the blowing up would be a zero section of M dual, where it's a rank E minus 1 bundle, and the codimension upstairs is also exactly E minus 1. So the ideal sheaf of the Y prime upstairs of the blowing up is also resolved by the Kousou complex given by the bundle M. Okay, so now we're in a situation very similar to like many other things, like the and we can compare that with the surge power of E, but when you're doing the twisting and push down, yeah. And then you can check easily push twisted by O of A and push down. You get the exactly the Eisenberg, the pushback Eisenberg complex. And exactness is just because all the higher direct image is equal to 0 in this case. It's a simple easy calculation involve the cohomology of M and the higher direct image of M. And then this implies that the complex is exact. As I said, that I mean all this work are basically modeled after the work of Kemp. I recommend the paper by Kemp. I mean, this is a paper in the early 70s by George Kemp. I think the title of the paper is like the geometry of the Riemann singularity theorem. So the classical thing is saying that you a Jacobian and you have the theta divisor in degree G minus 1, and you can measure the multiplicity of the point, each point, and at a point L, where L corresponding to a degree G minus 1 bundle, and the multiplicity is equal to basically H naught of L, where L is the corresponding to the point. And can give a very beautiful proof of that by studying the natural resolution of the singularity of the theta divisors and things of that sort. In this case, basically the symmetric product of the curve G minus 1 symmetric product map onto the theta divisor, and that is a resolution singularity. It's not a log resolution. In fact, often it's a small resolution, but that allows us, for instance, to deduce things like the theta divisor, the Jacobian has rational singularity and of that sorts. Okay. Now, so let's see our situation. We have the ideal generated given by some equation fi, and that corresponding to a map epsilon from O minus di to ix, and this should be a surjective map on sheath. And we do the blow up, and now we'll move the calculation to upstairs. And basically we map it, pull it up to the blowing up, and so we have a mapping from u prime, which is the pullback of u, and then we have a surjective map to u minus e. Now, the Eisenberg, the Buchsbaum-Eisenberg complex is exact in two situations. That X is the local complete intersection like what we described. The second case also exact is when the scheme is empty. And basically the Cousin complex in that case is always exact anyway, without worrying about whether they are regular sequence or not. And so we're going to do this in the case that the epsilon map u prime may have many equations. The u prime may be a very high rank, but you still see the u prime chosen by O of E will map onto OP prime. And then we can apply the case that when the scheme is empty, we can still apply the Buchsbaum-Eisenberg complex corresponding to epsilon prime. And then choose it by O of TH minus AE to compute. And the thing will sort of looks like this. Yeah, this the degree 0 part is C0, C1, C2, and they sort of looks like this. And now what we want to prove is the thing that the map of H0 is surjective. I mean, again, remember like the theorem that put together with Bertram and Lysenfeld before is about vanishing of higher cohomology. Here, this is really about surjection on H0. And so the calculation is a little bit different. I mean, and the shape of the theorem is also different. Before, only involved D0 to dE minus 1 involved only E equation. Roughly, this E equation is the thing cutting out the residual scheme. But roughly speaking, you need R plus 1 equation in order to generate the ideal. And that's why you need the theorem. In the theorem, involve D0 up to dR instead of just D0 up to dE minus 1. So we want to check that this map here is surjective on global section, and then you can identify upstairs and downstairs cohomology very easily. And basically, we just be due to asking whether this map on SA of U prime has OTH, and the Buchsbaum-Eisenberg complex map from degree 1 to degree 0, whether that map is surjective or not. You set the kernel of this thing like this, then basically it's asking H1 of the kernel is equal to 0. And again, just like quite a few calculations that we have done before, and you're just chasing back through the complex, and in this case, the complex is given by the Buchsbaum-Eisenberg complex. So we have something looks like this. So we reduce to putting Hi of Ci is equal to 0 for I equal 1 to R, and as long as T is bigger than this number, that desired number. Now, so then we come down to asking the cohomology of Ci. Yeah, and then we know that U prime is the direct sum of line bundle, so it's pretty easy. And so we need to understand the push, but the Laurent spectral sequence you reduce to computing something like this. The H0 of Hj of Rk, mu lower star OP prime of Lh plus T, something of this type, when the T is sufficiently large in the range that we want. Now, so again, let me just review this a little bit more. That X is a smooth variety on a smooth variety M, and of course dimension E. We have this blow up, and E is the exceptional divisor. Then I need to understand the push forward of O of E from O of AE from upstairs to downstairs, and I want to understand the direct image and higher direct image of these things. Now, if A is negative, then minus A, so you have something O minus AE, then it's well known that the push forward for O minus AE when A is positive is just the ideal shift to the A power. And the higher direct image is equal to 0. Now, what happened when the power A, you have O of AE, where A is positive instead of minus A, you have plus A, then what happened? Well, with degree 0, then we just push down to the structure sheaf. And for the high direct image, you want to check that between the fiber is P of E minus 1. Basically, you can see by, for the formal function theorem that between 1 and J minus 1, this thing all equal to E minus 2, this thing all is equal to 0. But you would see contribution from the high direct image for the RE minus 1 mu lower star or AE. And the assertion is that this thing is equal to some X group downstairs. Okay. Now, one way to prove it is to using Grothendieck duality. And this calculation is carried out most conveniently on the derived category. So on the derived category, Grothendieck duality can be expressed in such a form for any coherent sheaf on Y prime, and we just apply it to the case that the F is equal to O E minus 1 AE, and then it's not so hard to check that in fact this calculation show the lemma is true. Now, I'll leave it to you as an exercise to check the detail here. I mean, it's not so bad. Okay. Now, the power of I based on the structure sheaf OM, and then you have the X group. You have the XE minus 1. Then you flip everything around, yeah, IS of J, something like that, OM, and then you have in here, you have X E minus 1, IX of J minus 1 of OM, etc. Yeah? And you have the IJ J plus 1 to IJ. The co-kernel is the Sj of the conormal sheaf. And now, so what you see, if you have look at this, this is the thing I'm interested in. And each successive graded pieces, you can see that essentially by duality and the easy calculation, essentially this XE reduced to something of this type, XE of Sj of n due tensor OM. That's each graded piece of this filtration. And that in turn is isomorphic to Sj of normal bundle tensor, the determinant of the normal bundle. I'll leave it to you as an exercise to check that. It's not so bad. It's just basically this is equal to XE of OX OM tensor Sj of n, and then by adjunction, what you see that is this guy is the determinant of n. And now, so we need to prove that the xi of ci is equal to 0. And this in turn reduced to vanishing of the bundle of the form sk of n, tensor determinant of n, tensor O of L for L bigger than minus r. So we just reduce to this calculation about symmetric product of normal bundle and the determinant of the normal bundle. Okay. Now, it's somewhat amusing if you try to do the same calculation, but without assuming that the x is smooth. So suppose you have x is an m, yeah, and it's defined by some ideal b, x, but now this is some arbitrary scheme. Now kind of calculation is that you can check that the multiply ideal of B to the A, recall, is the, so you have the M prime. This is the log resolution of pair MX, and in here you have the exceptional divisor. And we're interested in computing RF lower star of O of M prime of AE, something like that. And I'll leave it to you as an exercise, maybe to compute this in terms of multiply ideals. Essentially, it's the same calculation. You just need to use the definition of multiply ideals together with the group predictability. I'll leave it to you to check that. Again, involve things like XJ and involve things of the sort. XJ. I mean, now you don't know the things called Macaulay, so you involve things like this, B to the A, and something like that, and then OM, something like that. I mean, the current calculation looks like something like this. Okay. Now, the vanishing that we need is pretty simple. You have the tangent bundle sequence, and then you have the sort of equilateral type complex resolving the thing. And this is for the symmetric product of N, and you have the symmetric product of tangent bundle map on the symmetric product of N, and then this is the complex resolving it, and we tensor the determinant N as O of L, and then this is equal to just the dualizing sheaf twisted by this. And so basically, we need to computing something like this. dp of tx, yeah. And so it's a reduced calculation of this type. And you see that the TP is quotient by O of M, and the kernel is just O of 1, and then the kernel is just rank 1 bundle O, and then the symmetric product of TP is resolved something of this type. This again is very simple to compute, and then you tensor this with what J of Tx, tensor omega x, tensor Ox of L, and using the J of Tx, tensor omega x is just the omega n minus j by the obvious duality, using the obvious pairing of, say, J of Tx pair with n minus j of Tx, then to n of Tx, that's determinant of Kx. This is equal to Kx inverse. Yeah. And things of this type is not hard to check. And now, then what the calculation then reduces something of this type. And this is precisely the Nakano vanishing theorem. And in turn, you can also see that this is as a consequence of the lattice hyperplane theorem from topology, and we interpreted topology in terms of the Horst group. And so this is it. And so this basically completes the proof of theorem 2. So it's the same philosophy at Kant, and you just reduce to saying that you have the Buchsbaum-Eisenberg complex, and you compute this on the blowing up. You resolve the basically O minus E or O minus AE by the Buchsbaum-Eisenberg complex, and then you proving surjective of section by proving the cohomology upstairs, and then compute the cohomology using the Laurent spectral sequence. Then the calculation reduced to question about normal bundle of X inside the projective space. And in this case, we're lucky enough that this thing reduced to just the classical Nakano vanishing theorem. And this allows us to prove the theorem. Now, for the TM4, remember that is about knowing the regularity of a reduced curve, and we want to compute its saturation degree. That is what TM4 is about. And this involves another trick that is somewhat similar to the trick that used by Gruson, Leistensfeld, Paskin in the regularity of the curve. Now, so in general, if you have a smooth variety and you have X inside M, and suppose you have a complex resolving the IX, so you have something like this, then Weismann proved that there is something called the Weismann complex, resolve the power of the ideal. Now, remember, X here is not something defined by regular sequence, so one does not expect to be something really nice, yeah. And so, but there, nevertheless, there's this Weismann complex, and this is how you construct that. This is the first few steps of the complex. Now, remember, I'm not asserting the complex is exact. In fact, the complex often is not exact. The first few map are the first map from SA of U0 to IX of A is the obvious map, yeah. And also the other one. And these are the first few steps are just the obvious map. And so in general, the case that the complex, you set CK of Uj is if J is even, is a symmetric product of Uj. If J is odd, then you define the exterior product, and then the I piece of the complex of the Weismann complex is just this direct sum over these graded pieces of this type. And for us, it's not so important really, except we just need to know that in our case, we can resolve the complex because we know M regular. So you can say that the first step is, this looks like sum of O minus N, and the next step is of the form of sum of O minus N minus 1. So we can bound the regularity of the Li and from the description. And if X is non-singular, then using the essential function, you can think of just like we know the resolution, minimal resolution in that case from the Buchsbaum-Eisenberg complex, though it's not so hard to prove that this statement, this complex is exact. And so we want to prove that this TM4, yeah, this is the statement, this saying the saturation degree is of the form A times M for I to the A. So we take the resolution and something like this. And basically, again, the question about saturation degree, again, reduces certain question to what's perfect certain section of H0 map onto the other thing. That is the saturation. That is how you relate it to. Now, we know the regularity of Li is is bounded by AM plus I, and just from the shape of the the shape of the Weismann complex, so we can bound the regularity of each graded piece of the complex. And now, so what you have is a complex is exact of X, and if X is non-singular, then at least the first few steps is really exact of just a few points. Yeah, and so that is enough to apply the following trick. Yeah, so you have a complex on the projected space and not necessarily exact, and precisely. So basically, the philosophy is saying that to chasing through cohomology of a complex, you don't really need an exact complex. As long as you have just some minimum knowledge about the homology, that will be enough to chase through the exact sequence by breaking it into both each step into short exact sequence involve the homology also. And I leave it to you as exercise to do this, to do lemma C. And this is saying that if you see the I homology of the sheaf has dimensions supported less than equal to something, yeah, and you have the regularity of the Li. And so what you need is that the Hi has dimension less than equal to I. Then you can check that the H naught of T to L naught of T again is surjective by the same kind of calculation. Basically, it just pretend that the complex is exact in some sense. That's because when you proving X naught is surjective is involved proving the H1 of the kernel shift is 0. But to something, if you have something that is mapped onto it, if the co-kernel is of 0 dimension, then the vanishing of the H1 of the co-kernel will already imply the vanishing of the H1 of the kernel. And that's enough. Basically, that is a philosophy. In our case, we know the complex is of exact off the curve. And for the later step, and the first few steps is exact only off a few points. And from that is enough to prove that the exact not H dot that's decided in our problem. And this is, let me just finish the talk here. So this proof that one can prove this the saturated span for reduced curve. A little bit, as I said, the proof is somewhat similar to the proof of the Poisson Weissenfeld-Paskin proof. Again, there they're getting some complex against some Igor-Markov type complex. Again, it's exact but not quite exact. And then is the philosophy there is the same thing, that even though the complex is not exact, but you can control the homology well enough. So that is enough to prove that the regularity, and here you get the regularity bound. I mean, this sort of non-exact complex is also involved like things like proving anti-property of high power for the adjoint line bundle, and this is the work that I did with Weissenfeld. And again, you have some complex, but the complex is not quite exact. But again, you understand well enough the homology. And if you can control the homology well enough, then you can pretend that it is almost exact, and you can still do the calculation. And that is enough for our purpose. So let me just stop here.